Hello again. In this video, I'd like to talk about abstraction. Abstraction is the art of simplifying an experience for a user. Technically speaking, it's the art of hiding unnecessary details from the user. Now you might be wondering what this has to do with computer programming or writing clean code, and we'll get there. But I first wanted to give an example from the real world about a dishwasher. A dishwasher is a perfect example of an abstraction. The user just sees a box and knows that they need to plug it into a power outlet and hook it up to a water supply, but they don't necessarily know how to fix it if something goes wrong. And so the details, the wires inside of the dishwasher or the tubes that are spraying out the water, those are going to be hidden from the user. A similar thing exists in computer code where we might want to hide details about the code from the user because it would make the user lose track of what's going on. And one thing to always remember when writing code is that your future self is the most common user of the code that you write. In coding, functions are the primary means of abstraction, and let's introduce that right here with a screenshot. The example that we can use is the ordinary least squares matrix algebra formula. This is something that's taught in introductory econometrics courses. Basically, we have this linear algebra formula for if we have a matrix of covariates x and our outcome variable y. This is how we estimate the least squares regression coefficient vector. We can do this two ways in our code. We can type out the linear algebra formula, or we can write a function that takes y and x as inputs, and then we label that this function is estimate OLS, and then it can return the coefficient vector that way. Now, why would we want to do this? This is a very simple example. And so you might be thinking this is a silly case where we would want to write a separate function for something that is so compact. But suppose you wanted to add functionality to, say, add a weighting matrix, or calculate robust standard errors, or calculate standard errors. You could add that functionality inside this function without really changing the user's experience with this line of code, but it would require a lot more lines of code in the unabstracted version. In Matt Gentzkow and Shapiro's coding guide, there are 3 rules for abstraction. The first rule is to abstract to eliminate redundancy. Second, we have abstract to improve clarity. And third, we have otherwise don't abstract. So what do we mean by abstract to eliminate redundancy? Let's go to a different coding example. In this example, we have an exercise calculating treatment effects in experimental data, and we want to get different treatment effects for different age groups of people. And this is a fairly simple mathematical formula where we just take the average of 2 different vectors and compute the difference, and that's going to be the average treatment effect. Where this gets a little bit tricky is that there's a lot of repetitive code here. So the way this works, this is Julia code, and basically we need to reference the column of the data frame. That's what these colons are doing. And then the first argument in these square brackets is subsetting the rows that we want to look at in our data. And where you can see this might cause a problem is this blue line that's underlined, this blue underlined area. That is highlighting that there's a spelling error here because it's sensing that it's not the same as these other situations. Now, why is that detecting? Well, it's because I have some add-ons in my VS Code that are making that functional. If I didn't have VS Code and this was just a plain text file, I wouldn't be able to capture this error. This would be what we call a silent error, and then we would eventually discover the problem, but we'd have to rerun the code and get a runtime error in order to know what problem was. So what's the solution to this problem? Well, we write a function, and in just 5 lines of code, we can have a function that calculates the average for the treatment group, the average for the control group, and returns their difference. And then we can subset on the conditions. So not only is the code up here repetitive because it is doing the same sort of calculation of the difference in the averages, but it's also repetitive because for the treatment and control, we have to give it the same set of rows. And so when we write this in a function, we can abstract it by just saying, okay, user, tell me the condition, and I can apply that condition equally to both the treatment vector and the control vector. And then we can get our end result in about 10 lines of code total. That's about the same number of lines of code that we had before, but it's much more structured now, and it's easy to just add a different subset calculation. Let's talk about rule number 2 now. Rule number 2 is to abstract to improve clarity, and let's go back to our OLS example from before. So here we just have a linear algebra formula, but it's a linear algebra formula with not much context as to what's going on. Whereas if we instead turn this into a function, we can use the name of the function to clarify what's happening. So if I execute this function, I'm going to calculate the OLS coefficient vector. And then finally, let's talk about when we shouldn't abstract or when it is over abstraction. And for this, we'll use another example. Actually, for this, we'll just talk through it. We could, instead of using the plus sign to add two elements together in our code, we could create a custom function called add up and just apply that to both of the elements that we're adding together. That would be an example of over abstraction because seeing the plus sign in the code, the user already knows what's happening. And if they instead saw a custom function called add up, they might be confused about what's happening. And so that's an example of overly abstracting and ending up confusing the user in the process. One last thing that I'll point out is about function scope. So let me load up another screenshot. When you define a function, it's going to have a scope. And what we mean by the scope is whatever gets passed to the function, that's all that's inside the function. That's all that the function can see. So if we have our estimate OLS function that we just barely talked about, we can call the inputs to the function whatever we want. Usually we would want to call them things that would be natural for the context that they're being used. But the point is that these objects, yvar and xmat, they're only going to be existing within that function. And so if I were to try to call this function using the variable names that are in the function, it probably won't work because I probably don't have objects in my workspace that are called yvar and xmat. So that's just a little reminder about how functions work and how abstracting works. Whenever you're abstracting, you're creating a variable that only exists within the function, and then when the function gets called, whatever you pass to that function gets coded in as that variable. So what's the right amount of abstraction? That is a subjective question. Different programmers will have different opinions about which type of code is optimally abstracted. And if you're just starting out, I would err towards the extreme of not abstracting and having redundancies in the code. This, in the past, has helped me understand the patterns that the code needs to respect in order to be abstracted optimally. But it depends on the particular situation that you're in, how much you want to start with the redundancies, or how much you want to start jumping into having a function for everything, which would be the other extreme. I hope this video has helped you a little bit to understand better the notion of abstraction and how it can be useful in clean coding. Up next, we'll talk about documentation and unit testing and some other parts of the workflow for clean coding. Thanks for joining.